So here we go, chapter 3.6, example 18, continuing with this summation notation. So let's have a look. Find the value of. So the question is basically the same as the last one we had. Whoops. 12, k equals 1 to 12, 5 times 3k minus 1. So we just start. We've got 5 lots of, substitute the k equals 1, 3 to the 1 minus 1 is 0, plus 5 times 3 to the 2 minus 1 is 1, plus 5 times, when k equals 3, take away 1, we get 3 to the 2. Keep on going. Last term will be 5 times 3 to the 11. Now, what do we notice this time about the series that we've generated? To get from this term to this term, we've multiplied by 3, multiplied by 3, etc. So what kind of sequence is this? Well, if we're multiplying by c, we should recognise this as a geometric series. And you can see that this kind of shape, 5 times, the base 3 to the power k minus 1, generates a geometric series. So we should be thinking about the sum of the first n terms of a geometric series is a times, what do we notice about r here? The modulus of r is greater than 1. These values are our r values, aren't they? Because it's a common ratio that we've got. So r is greater than 1. So we want the version here where we've got r to the n minus 1 over r minus 1. Because we don't want to work out each term separately, especially as you get larger numbers of terms. So Sn is equal to a. Well, the first term is 5 times 3 to the 0. Well, let's just list these out. A must equal 5 times 3 to the 0. 3 to the 0 is 1, so that's 5. Our common ratio r, we've already identified as 3. And the number of terms is 12, the minus 1 plus 1. Right, it's the difference between the top and the bottom of our sigma signs plus the 1 to get the right number. Okay, so we get 12 for n. So 5 times 3 to the 0 is a. So we've got 5 r, which is 3 to the 12, take away 1, over 3 minus 1. Tap that in a calculator. It's going to be fairly big. Not sure, a million-ish. Let's tap it in. 1328 600 over 2. Sorry, not over 2. That is the final value in the calculator. So that's part A. Part B. We're going to get the sum from k equals 5 to 12 of 5 times 3 to the k minus 1 equals. Now the key thing here is to notice very carefully the top and the bottom values of k, because the other equation, this part, is exactly the same as we had before. So we've got 5 times 3 to the 4 plus 5 times 3 to the 5 plus up to 5 times 3 to the 11. So go through, we recognise as a GP, yeah, times by 3, etc. Therefore it's a geometric series. So A is equal to 3 to the 4 is 81 times 5. So 5 times 81 will be 405. R is still equal to 3. How many terms have we got? Well, it's not just the number at the top, and this is why I've been going on about this from the beginning. It's not 12, it's 12, take away 5, which is 7. Yeah, but then we need to add the 1, because you've got to count both ends. Yeah, whereas if you do the subtraction, you just find the difference, but you've got to include both ends, the term 5 and the term 12. So we get 7 plus 1 is 8 terms. So Sn equals A lots of r to the n minus r to the n, take away 1 over r minus 1. And we're using that because the modulus of r is greater than 1. Substitute in 405 times 3 to the 8, take away 1, divided by 3 minus 1. Tap it in the calculator, and although we've lost quite a lot of terms, the terms we've lost are from the beginning. It's the first 4 terms. Well, they're the smallest, so the number's still going to be up in the millions. Yeah? Tap it in the calculator, and it wouldn't surprise me if it's very similar. Yeah? And we get 1, 3, 2, 8, 4, 0, 0. Okay, so almost exactly the same, certainly the same to 4 significant figures as the original answer. Well, 3 significant figures.